Okay, good morning and welcome to this course on real-time systems. Today we will have some introductory discussion on real-time systems and we will see what are the topics and so on. Possibly in the subsequent lectures we will discuss in more detail. So, let me just introduce myself because some of you I am teaching for the first time. So, I am a professor at the Department of Computer Science and Engineering, IIT Kharagpur, been with IIT Kharagpur for last about 16 years and before that worked with Motorola India and completed all my education, bachelor's, master's and PhD from Indian Institute of Science, Bangalore. And as the course proceeds, possibly based on the questions you ask, we will just get to know you about you, your name and so on. So, let us start. Let us look at the plan of the course. We will have one or two or maximum three lectures on introduction and then we will look at some very basics of real-time operating systems, because that is the major emphasis of the course, real-time operating systems. And as we will see that scheduling tasks is one of the major issues in any real-time operating system. We will look at uniprocessors, how tasks are scheduled. There is quite a bit of theory developed over the years for task scheduling in uniprocessors. Possibly you have done in an operating system course, basic operating system course, how tasks are scheduled in a traditional operating system. We will see that here is different, we will observe the difference and we will look at multiprocessor and distributed system. We will look at resource sharing issues and after that we will look at commercial real-time operating systems, some of the operating systems that are actually used in different organizations. And then we will look at real-time communications, because nowadays most of the real-time systems they have they communicate with other devices or maybe on the internet. So, we will see how real-time communication can be supported and then we will look at real-time databases, because increasingly more and more these systems are using databases to store data about their environment, process them in real time. As you can see, the plan of the course, it is mostly deals with software issues. We will restrict the hardware issues to minimum. We can't really avoid in such a course some hardware issues, but we will restrict that. Otherwise, the course will be too large. So, the textbook will be a book I wrote on real-time systems, 2008 Pearson publication, and the book will be supplemented with some handouts that I will give you periodically. Now, let us look at the grading issues, because in any course grading is important. Class test 1 will have 10% weightage, which will occur sometime end January. Mid semester will have 25% weightage, sometime around end February. Class test 2 will have 10% weightage, sometime end March, and the end semester will have 50% weightage, sometime in the end April. So, as you can see that almost every month end we have one test or other, just to keep track whether you are following the course or if there are any specific difficulties. We will give you feedback on your performance. And another thing that we will follow here is that as the course proceeds, we will pose you some problems. The problems are not there, I mean the answers are not there in the book, neither can easily get them on a Google search or something. Basically, you will have to think. So, those who are able to do those problems will have additional mark more than this whatever is displayed here. So, that will be added to the total more than this 100%. So, based on the 100% and the IIT grading scheme, like all of you are familiar, 90 above EX, etc. We will follow that. But one thing is, yes, please. 5% okay, yeah, okay. I think he has pointed out good thing that we have only 10, 25, 10, 50 is 95, and he says that 5% are not mentioned. Yes, 5% is an attendance. Yeah, possibly I should have written here that just to encourage you to attend every class, we will have 5% weightage given to attendance. If you attend all classes, 5% is assured. Actually, grading as you know that grades are not really a indicator of the intellectual capability or something, because even the best students can score poorly, they do not study, do not attend classes. As long as you are putting effort on this course, keeping track with the lectures, should be able to get good grades. So, let us look at how the technology has advanced over the years. We will see where the real time systems come in. In the 1960s, the computers were basically mainframes, extremely expensive computers. Hardly an organization or institute owned one, and the students or the employees will use that, and these real time systems and embedded systems did not exist those days, because they were extremely expensive for everyday use. And then in the 70s we had mini computers. These were also expensive, and in 1980s we had the personal computers where the cost dropped dramatically, and computers got used across various domains, and this is the period where the embedded and real time systems, the use started to increase. And in 90s we had the mobile phones and internet. This was the revolution in 90s. Suddenly everybody started using internet, and mobile phones, as you know, appeared around in India 95 or something, and then now you know everybody owns a mobile phone, students or a shopkeeper or even the rickshaw pullers in Kharagpur, they own a mobile phone. And now one thing that is clear now is that embedded devices, that is after 2000, these are vastly outnumbering the traditional computers. So, if you look at the number of processors manufactured worldwide, the number of processors being deployed in embedded devices is about 70% of the processors manufactured. And we now have internet enabled embedded devices. For example, through the internet you can download code onto your devices, they are connected, you can control them on the internet. So, we will look at these as we proceed, we will look at several examples of this. So, the embedded devices are basically, they use real time operating systems, they are a type of real time systems. We will see what are these real time systems, real time operating systems, some basic concepts about that. So, as we just saw that the embedded systems are being increasingly used in new applications, and all these have real time in nature, in the sense that based on some events the action must take place within certain time. The number of processors that are manufactured worldwide now vastly outnumber, I think I said about more than 70%, that is the statistics published. Out of the total processors manufactured, more than 70% being used for embedded applications. But over the years, why is there a surge in use of embedded applications? There are many reasons actually which have contributed to this trend of increasing use of embedded applications. One is, of course, the cost of the computers has decreased over the years. from million rupees to few thousand rupees over about 30 years or so. The processor cost has decreased, memory cost has decreased dramatically, both the semiconductor memory as well as the magnetic memory. And as you will see that in real time systems, actually the magnetic memories are not used that much. We have the flash memories that are being used. And then the flexibility that has come about due to the use of internet, the embedded devices, even though they are small and many in number, but you can easily configure them, you can maintain them through internet. And another important factor that has helped increase the embedded application is the reducing power consumption that is seen over the years. Actually, many of these embedded applications, they are battery powered, and unless they consume less power, no, they won't be usable. And size has reduced from the size of a room to the size of a very small size. And we have not only that, we have increased processing power, and the reliability of both hardware and software has increased considerably over this period of time. Now, let us see some examples of these applications, so that our later discussions will fall into place. Like when we say that some kind of applications we use a time based scheduling, and in some other applications we use a event based scheduling, why etc., that will become clear, and even databases, communications and so on. We have large number of examples. We examine actually a few examples here. The set top boxes, mobile phones, iPods, PDAs etc., are all examples of embedded systems, and we will see that they use various types of real time operating systems. One example is the modern car. A high end car can use more than 100 processors which are embedded in various parts of the car, and complex software run on this, and some of the high end cars have code up to 1 million lines. Now, what do these processors do? They do engine and emission control, traction, carrying out some diagnostics and giving early warning of problems, automatic transmission and so on. So, as you can see here that there are processors at various places in a car which do various activities. Even I think it won't be wrong to say that in the present time you won't find a car on the road which does not have processors in them. There are large number of embedded systems and the ones that run these real time operating systems. Some of them are difficult to, unless we say that these are devices which have computers, which have processors and software, real time operating system, you won't really notice them. For example, look at this laser printer, use it every day, but there is a processor which does some activities. We'll look at that. For example, let us say these toys, or a coffee machine, or a phone, handheld phone, or a radar, or a internet router, all have all use. Yes, please.
What is the difference between a processor in a computer and a processor in such devices? Both are processors. Why is this called a real time system?
Okay, yeah. See, the question is that, let me just get the question all right, that there are, even in a PC or something, we have a processor and we have software running on it, which are computers basically. So, what is special about these devices? Why do we call these as real time systems? Okay. So, that is a very basic question, and we have some slides coming up on that, because that is the fundamental question we must answer, that what is the basic difference between a PC or a mini computer or a workstation versus a real time system. We have some slides. So, let us try to answer this with the help of slides. Just have patience for a minute or so. Now, let us see what is this real time, then we will look at what is real time system. One is that in a real time is one where we quantitatively measure time using a physical clock. In the contrast, we have a qualitative time where we say that something occurred before something, we do not know how much before, or something occurred after, or something will occur sometime, something will occur eventually. If you use these terms to describe a system, it will be non-real time. Whereas, if you say that a certain event occurs, for example, in a chemical plant, that when the temperature exceeds 500 degree centigrade, the corresponding action, that is a coolant shower, should complete within 100 millisecond of the temperature exceeding. So, we have a notion of time here with respect to a physical clock, which measures this 100 millisecond. We will see more examples, and we will also contrast this with traditional computers. Now, let us look at some of the applications. We have large number of applications. We will not mention all of them, it will consume all our time if we just try to discuss these applications. We will just give some example applications in each area, and possibly in a later slides we will just look at couple of them in some detail. The idea is that we will try to find out what kind of tasks they run and what is the timing constraint on those tasks. Let us look at the industrial applications. A chemical plant control, as we are saying that a chemical plant has many parameters. The rate of chemical reaction depends on the chemical concentration, temperature and the pressure, and based on these parameters changing, the rate of the reaction might vary. So, to control the reaction, we will have to monitor these parameters and then also control these parameters for the chemical plant to operate. Let us look at a automated plant. Let us take an example of a car assembly plant. I do not know whether you would have gone to a modern car assembly plant where many of the activities are automated. You go to a car assembly plant and find that there are very few persons there visible, but there are systems, there are partly completed parts of the car moving on a conveyor belt, and there are workstations where the workstations are doing work on these partly completed parts of the car. So, here there is a computer control of these various workstations and also the synchronization between these various workstations. Supervisory control and data acquisition, this is a very important industrial application where you monitor various parameters of a system which is distributed. Just to give an example would be an energy management system where you try to balance the load in an electrical system, because the consumption by the customers is unpredictable, and unless the electrical power is balanced, the line will trip, right. So, you will have to monitor the power consumption and apply load shedding, and also give this feedback to the generator, possibly to keep up with the power generation. medical, most of the medical equipments actually use processors and software. Medical electronics is an important area for real time systems. Another use may be use of robots to do, there were reports in newspaper that robots are even able to do some operations for precision, and some activities which are difficult by human beings being done by robots. For example, let us say radioactive treatment, and sometimes the radioactive material gets displaced from the machine. A human can go and put it back. It will be a robot which sets the material at its right position. Different peripheral equipments now we see that are attached to a computer. Most of them have embedded applications. For example, laser printer, use them every day, but what we do not see is that the processor that is there and the activities it does to give us this nice print, we do not see that. Similarly, digital cameras get signals and processes them and stores them, later transferred to computer. Camcorders, some types of sensors. Similarly, in the transportation, these are used heavily. The MPFI system, now I think all the cars to be roadworthy, they have to use an MPFI system because they reduce the pollution. Here the idea is that when a computer controls the exact fuel quantity and the time of injection of the fuel, the car will run at maximum efficiency. So, at multiple points the fuel is injected depending on the values of the car speed, the acceleration, and the other conditions like temperature and so on. Compared to a carburetor based system, here the efficiency of petrol, efficiency of combustion is much higher, and this has made the carburetor system obsolete. This we will see little bit about that. And then the automated car, where a car is driverless and being driven based on the sensed signals on specific roads. So, there are reports that the automated cars are able to cover distances up to 60 kilometer. I mean, there is every year a competition for automated cars, and even on crowded streets they are able to drive. So, possibly in few years we will have them in our streets as well. Telecommunication applications, important example is the cellular system, the mobile phones that we use, the base stations that are there which receive our signal from the mobile phone and give signal to the mobile phone, they use real time operating systems. They handle many tasks any time. For example, handling SMS messages, handling call establishment, keeping track of billing, handoff to other base stations and so on. Similarly, the mobile phone itself has a real time operating system. We will have quite some discussion on that later on, the different activities that occur inside a mobile phone and how these are handled and the kind of real time operating systems used in these mobile phones. Most of the aerospace applications now indispensably have computers on board, because these reduce the botherance of the pilot, right? They help them, and sometimes even without pilot they can fly the aircraft. The internet also uses many embedded systems. I was just giving you an example of a router. Multimedia applications, for example, video conferencing, handling the signal, compressing, transmitting, receiving it on the other side real time, because in video conferencing, if there is a one frame to another frame, if there is a the time delay is not proper, you will see glitches and you will say that it is not working. So, these are also real time systems. Then consumer electronics like phones, digital cameras, camcorders, defense applications. In defense also these are used heavily, including the wireless sensor networks. Now, let us look at couple of them in slightly more detail, just to know the kind of time constraints under which they will have to work and the kind of tasks that are involved. Let us look at the automotive application. So, 30 to 90 processors per car is nothing unusual, that was in 2005, and the kind of activities they do is engine control. I was saying that the fuel injection is one important work, the braking system, airbag deployment, because in case there is accident, within fraction of a second the airbag has to be deployed, it has to be inflated and it has to be deployed, otherwise it is of no use. Even the windshield wiper, these are even use processors, depending on the rain intensity, they can manage themselves without the driver intervening. The door locks, the entertainment systems, the diagnostics that run on this, for example, measuring the tire pressure and giving early warning, measuring the health of the other critical parts. So, these are done by various processors. One example is a high end car, the BMW 745i, which has 2 million lines of code, uses the Windows CE operating system. We will discuss this operating system in some detail later as we look at the commercial operating systems, commercial real time operating systems. It has various types of processors, 53 8-bit processors, 11 32-bit processors and 7 16-bit processors, and inside the car there are many networks. Now, this is another automotive application, almost every car has this, a multi-point fuel injection system. Just see here, there are different points at which the fuel is getting injected, and the quantity of the fuel and the time at which the fuel is to be injected is controlled by the computer. These are determined based on various signals received from different types of sensors. We are saying that the sensors are the speed, the RPM, revolutions per minute, the temperature, the acceleration and so on. Earlier the mechanical system in a carburetor, no, you need to tune the car every once in a while, so because that used to go out of tune, and it was inefficient. You can't really do whatever is done by sampling various events and then taking action based on that and quickly computing how much fuel to be injected and time to be injected and the different places. See here, multiple points where how much will be injected. A laser printer, use them, we have used them many times, but there is a processor inside and it does some activities. There is a horizontal strip of dots that needs to be composed. The basic capability is to print a dot, and if you have a PostScript file or a text file or files in some specific, I mean for different laser printers, they have specific languages in which the fonts are specified. So, depending on the font, that has to be translated to dots, and this is done by a image processor, and then these are transferred onto a rotating drum inside the laser printer. The image is transferred in the form of charges, and a laser beam is used to neutralize charge from the black parts of the image, leaving only the static electric negative image on the photoreceptor surface, so that when the ink powder is spread, it gets attached only to the charged parts, and then these are transferred to a paper through again through electric deposition, because there will be a opposite polarity electric charge which will attract the electricity from the drum, and it will get deposited on the paper. And then the next thing is to fusion, where you have this temperature. You see that paper coming out, printed paper is hot, because after the ink is deposited, the ink powder is deposited, these are fused through heat onto the paper. A mobile phone, I think we did not talk about the timing here. The timing depends on the speed of the laser printer, but typically most of these tasks need to be completed in millisecond. So is the case for a fuel injection system. Milliseconds is the time for different tasks, tens of milliseconds to hundreds of milliseconds. A mobile phone, all of us have used it. So why do we need an operating system and a processor in that? One is that to convert the voice to digital using DSP techniques, and then convert the digital voice to signals that can be transmitted at the CDMA, modulated signals, code division multiple access. And also once the signal comes, this has to be converted to the microphone signals. And also, see, these are the signals which are the voice signals, but there are also some control signals that are received from the base station. For example, the position, and when you are mobile, the base station needs to register the mobile phone, or when you switch on a mobile phone, there is a transmission on the control channel. Similarly, to send an SMS or to handle user invoked functions, the user might do like set alarm or do several of the provided operations on a mobile phone. So all these are handled by a processor. So if you look at these different parts here, there is a memory, there is a processor here. Unless I enlarge this image, you can't see this, but as I said, at later part we will discuss in more detail. SCADA is an important industrial application, stands for supervisory control and data acquisition. So the data arise at various places geographically, and these data are collected at different places, and even they might be stored at different places by a real time database. So these form a distributed real time database, and then the required information only is transmitted to the supervisor, and the supervisor can give commands to the different local monitors to take certain corrective actions. As we were saying, that one is an energy management system, where you try to balance the load in electric lines, or maybe a building management system, where the timing at which the various lights are switched on and managing the power inside a large building is also a SCADA application. Computer on board an aircraft. So as we were saying that the velocity, acceleration and altitude, these need to be sampled by using some sensors, and based on these values of velocity, acceleration and altitude, the position of the aircraft is computed, and the deviation from the required trajectory is computed. Based on the error in the trajectory, planned trajectory and the current trajectory, some corrective actions need to be taken through the actuators. And again here, the rate at which, the constraints on the tasks will be again in the form of milliseconds. The rate at which these are sampled, the rate at which the tasks need to be completed of the order of milliseconds. A missile guidance system, this is a defense application where let us say the defense system senses a missile from an enemy and then send an anti-missile that is guided, it just tracks that missile and destroys it. It tracks it based on some thermal and electrical characteristics, and once it tracks that, the trajectory of the tracked device is computed and then the track corrections are based so that it will directly meet that and destroy that. So, here the constraints are of the order of micro to few millisecond, because these travel at very large speeds. So, the time also needs to be that much smaller, the activities must occur in microseconds. So, we saw some of the applications and found that in each of those applications there are many tasks that need to be completed, multiple tasks running at the same time, and the constraints are of the order of milli to microseconds. Now, let us look at the trend in these kind of devices. So, one is that the computational demand on many of these devices is increasing rapidly. Just to give an example is a video conferencing, where you want good quality picture and also voice among multiple participants to be transmitted and heard, which is very large compute intensive, because all this image and data had to be transmitted at a very fast rate to give good quality. And similar is mobile TV, or on your mobile phone, let us say you want to see TV. The mobile phone processor must be capable of processing the signals and be able to show it. So, one is the increasing computation demands need more powerful processors. The other is most of the devices now are networked, so that we are able to remotely monitor and debug these various devices. We can see whether these are working in proper condition, have failed, we can know the reason they have failed. They can have even web connectivity, web browsers, for example, some cars have web browsers. We can have cameras, disks that are networked. You do not have to really plug them in to transfer data, they directly sit on the network and you can download the data or get data from computers. And not only that, we have another constraint which we will also discuss while discussing about the real time operating systems, is a commercial issue that because of the increased competition, the different companies want to market their products the quickest possible, and also specific hardware and software needs to be designed for some of the applications. We will just see shortly about that. Now, let us see a basic model of an embedded system, because we just said that embedded systems are a major category of application for real time operating systems. There are other applications of real time operating systems other than the embedded systems. Even certain large computers might use real time operating systems, but let us look at an embedded system, because unless we have some idea of them, later discussions won't be very meaningful. So, what every embedded system does is, it has sensors which it samples some signals, different sets of signals, and the signals are either very low voltage, low current, or this may be a direct current direct voltage, or this may be alternating. So, there are various types of voltage and signals that are sampled, and therefore, we need a conditioning unit, because our computer recognizes voltage and current at certain values. So, the input interface does that, connects these sampled voltage and current to the input interface, and the real time computer, they process this signal, and of course, there is a human interface where these are monitored, configured and so on. But normally the human interface is not used very frequently, unlike in a traditional computer. Here the operator only intervenes only if there is a extraordinary situation or to initial configuration and so on. And the actions of the computer are carried out by the actuators. Again, these require different amounts of voltage current as is produced by a computer. So, we need conditioning units, voltage scaling, be able to drive a motor and so on. So, let us have some idea about the sensors, because even though these are not crucial to real time operating systems or real time systems by themselves, but unless we have some idea, we do not know what kind of signals, what kind of voltage levels etc., we are talking of. As we are saying that these sensors convert physical characteristics into some electrical signals. One example is a photovoltaic cell, which converts light energy into electric energy. The electric energy is in terms of millivolts, milliamperes or maybe microamperes. We can have temperature sensors which sense the temperature based on the thermocouple principle. There can be pressure sensor which operate based on the piezoelectricity principle. Again, all these generate some electric energy and typically millivolts. We now commercially have several low cost sensors that are available. The IR proximity sensor, the soft encoder, GPS, sonar, infrared distance sensor, electronic compass, CMOS camera. See the camera mounted here. So, these are various types of sensor you can buy off the shelf from shops, and these are used to build the embedded systems. These are some of the actuators which convert electrical signals from the computer into actions. The actions can be in the form of a motion, changing the thermal characteristics or electrical characteristics, pressure, physical characteristics, so on. Some of the popular examples are motors, heaters, hydraulic and pneumatic actuators. So, there is no dearth of examples for sensors and actuators. There are many of them. If you examine any device, let us say camera, or let us say a laser printer, or let us say a mobile phone, you can see the different types of sensors and actuators that are needed. So, this is a low cost servo used in many applications, including the robots. It is a small wireless device, has a shaft, and this can be positioned at specific angular positions by sending a coded signal, very popular in robots. So, as the signal exists, it will maintain a position, otherwise it will change the position. We will not go into details of this. These are beyond the robots, it are used in controlled cars. some toys. Now, let us have some small idea about signal conditioning, even though not really a crucial part of the course, but just to have the idea about what these sensor signals are done before they are processed in the computer, or the computer signals, what happens to them before these are given to the actuator. So, signals in millivolts need to be scaled up. So, we need voltage amplification, and sometimes we need voltage level shifting, because the level of the voltage is let us say between 10 to 20, what we need is -5 to +5 or something. So, we not only need amplification, might need level shifting, we might need frequency range shifting and filtering, and the mode conversion AC to DC and so on. And of course, most of these devices they use analog to digital and digital to analog converter, because most of these sensors they generate analog signals, whereas our computer needs digital signals, and similar is the case with respect to actuator. Most of the actuators they need analog signal. So, a digital to analog converter needs to be done. Again, these are available off the shelf. See here a small chip here, it's doing analog to digital and digital to analog. So, with that basic introduction to various areas where these real time devices are used, and the basic definition of what is real time, that where the actions need to take place based on some physical clock events generated by a clock, and also the other events generated in the system. So, let us look at what is a real time system. If you have a system where to describe its behavior, you need to resort to some real time description, need to implicitly or explicitly use timing aspects. That is a real time system, but just remember that we do not have to really use in every behavior, even if some of the behavior of the system requires some timing description, that is a real time system. Actually, most of the real time systems that we will discuss, not all tasks are real time. For example, we have a logging task, which keeps track of different events that occurred, actions that were taken. These occur non real time, no constraints on that, they can be completed as and when required. So, one issue we need to just mention here, that we said describe the behavior of the system, and if you need a timing issue there, need to be measured using physical clock. It is a real time system, but what exactly is a behavior and how do you describe? A behavior is the input output processing. When you give a input, how does the output, what output occurs, and how does that input gets transformed to the output? That is exactly is the behavior. So, to describe the behavior of a system, we will have to find out what are the input to the system, what signals or what data was input, and what did the system do to generate the output. That is the behavior, and to describe that, if we need timing issues, then that is a real time system. Now, in the next 1 hour or so, we will try to find out some important characteristics of these systems, because based on these characteristics, we will have to design our operating system, because the operating system must facilitate that these devices they stick to their characteristics, otherwise they will fail. One of the important characteristics is timing, responding to event in certain time. So, the events are obtained through the sensors, reported to the computer. These are the input event, and somehow they need to be processed and some output produced before a certain time expires. For example, if a robo senses a obstacle and the robo is progressing, moving, and unless it changes its track, it will collide and the system will fail. Another example is automobile airbag system. I think we are just mentioning about it, that once the sensors detect a collision, the system must respond. The bag must be inflated, must be deployed within 10 milliseconds or less, otherwise it will serve no purpose, because the vehicle is typically in speed and the damage will be done even within a fraction of a second. So, there are some discussion left on these different characteristics, and also this the basic configuration of a embedded system. We need to have some idea about the CPU, the kind of memory, the kind of sensors and actuators, diagnostics, human interface, etc., so that we will be able to appreciate our real time operating systems. And when we mention that event occurred millisecond interval, we will have idea about what kind of events and how actions take place, what are the constraints on the memory, constraints on the CPU, constraints on the software. So, we will continue from this diagram in the next class. We will stop here.